Picture this, an invisible skeleton stretching across the cosmos, holding galaxies together like beads on a string, yet no one has ever seen it directly. This is the cosmic dark matter web, the hidden architecture of our universe, and it's one of the most baffling enigmas science has ever faced. We've mapped stars, traced the paths of planets, even peered back to the edge of time itself, but dark matter refuses to give up its secrets. It doesn't emit light, absorb light, or interact with anything we can detect, and yet without it, the universe as we know it would fly apart. What if I told you that everything we see, every galaxy, every swirling nebula, every flickering quasar, is just the tip of the iceberg? That the real story of the cosmos is written in something we can't even see. For decades, scientists have been piecing together clues, chasing shadows in the dark, and what they've uncovered is a web so vast and mysterious, it redefines our understanding of reality. This isn't just a handful of unanswered questions, it's a labyrinth of 25 cosmic mysteries, each one more tantalizing than the last. How does this invisible web shape the universe? What strange forces are at work in its hidden threads, and why, after all this time, does it still slip through our grasp like smoke? That's where this journey begins. Together, we're going to venture into the depths of the unknown, unraveling the secrets of the dark matter web, one mind-bending puzzle at a time. From ghostly particles that pass through you right now without a trace, to colossal structures lurking in the void between galaxies, this is a story that challenges everything we think we know. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Scientists have a name for one of the most unsettling truths about our universe. The stuff we can see, the stars and galaxies and cosmic dust, makes up less than 5% of everything that exists. The rest is dark matter, an invisible force weaving through space like ghostly threads binding the cosmos together. Think of it as the universe's hidden framework, the steel beams inside a skyscraper you'll never see, but without which the entire structure would collapse. Here's how we know it's there. Galaxies spin so fast that, by all known laws of physics, they should tear themselves apart. The math just doesn't work unless something unseen is holding them together with an extra gravitational pull. That's dark matter acting like cosmic glue, keeping stars from flying off into the void. And it's not just individual galaxies. Look at the largest scale imaginable, and you'll find entire clusters of galaxies moving in ways that defy explanation unless we account for this invisible scaffolding shaping their path. One of the strangest clues comes from something called gravitational lensing. When light from a distant galaxy passes near a massive object, its path bends, distorting the image like a funhouse mirror. But sometimes the distortion is far stronger than the visible mass should cause, as if something massive but completely transparent is warping space-time itself. That's dark matter again, bending light with its unseen gravity, leaving fingerprints in the empty stretches between stars. The story starts nearly a century ago when astronomer Fritz Zwicky first noticed something odd about the Coma galaxy cluster. The galaxies were moving too fast, as if tugged by something invisible. He called it Dunkel Materie, a dark matter. Most scientists brushed it off at the time. Then in the 1970s, Vera Rubin's painstaking observations of rotating galaxies confirmed it. There had to be more out there, something we couldn't see. Now here's the twist, we still don't know what it actually is. Particles, wispy filaments, an entirely new kind of physics. Every time we think we're close, dark matter slips away, leaving us with more questions than answers. But one thing's certain, without this invisible architecture, the night sky would look utterly different. Galaxies might never have formed, stars might never have ignited. And we, tracing its shadowy outlines from our tiny corner of the cosmos, wouldn't be here to wonder about it at all. Imagine watching a merry-go-round spin so fast that the kids clinging to its edges should go flying off, yet somehow they stay firmly in place. That's exactly what astronomer Vera Rubin saw when she studied the motions of galaxies in the 1970s, and it shattered our understanding of the cosmos. The outer stars in spiral galaxies were whirling around their centers at speeds that defied the laws of gravity as we knew them. According to Newton and Einstein, those stars should have been flung into the void, their velocity far exceeding the gravitational pull of all the visible matter in the galaxy. But they weren't. Something unseen, something massive was holding them in place. Rubin's meticulous observations revealed a truth as unsettling as it was undeniable. The universe is filled with missing mass. The stars, gas, and dust we can see account for just a fraction of the gravity needed to explain how galaxies move. It's like weighing a suitcase by how hard it is to lift, only to open it and find it half empty. The numbers didn't add up, and Rubin's work became the smoking gun for dark matter's existence. This wasn't just a small miscalculation. In some galaxies, the discrepancy was staggering. Up to 90% of the required mass was simply missing. If you added up all the glowing stars, nebulae, and cosmic dust, you'd still be left with a gravitational void. The only explanation, an enormous halo of invisible matter, enveloping each galaxy like a shadowy glove, its gravity gripping the stars tighter than anything we could see. But here's where it gets even stranger. The dark matter isn't just sprinkled randomly, it's woven into the fabric of the universe in precise, predictable ways. When scientists mapped the rotation curves of countless galaxies, they all told the same story. The speed of stars didn't drop off as you moved toward the edges, as classical physics would predict. Instead, the curves stayed flat, meaning something unseen was exerting influence far beyond the galaxy's visible edge. It was as if every spiral galaxy was just the glowing tip of an iceberg, with the real bulk lurking beneath the surface of our perception. Rubin's discovery didn't just add a new chapter to astrophysics, it tore up the old playbook. Suddenly, we had to confront the possibility that everything we thought was solid and visible in the cosmos was just floating atop a hidden ocean of darkness. And yet, for all its mystery, dark matter's effects are everywhere. It sculpts the paths of galaxies, bends the light from distant stars, and even guides the birth of cosmic structures. We may not see it, but its signature is written across the sky if you know where to look. What if we've been searching in the dark for an answer that isn't even there? The hunt for dark matter hinges on one assumption, that our understanding of gravity is complete. But what if gravity itself works differently on cosmic scales? That's the bold claim behind modified Newtonian dynamics, or MUND, a radical alternative to dark matter that's been turning heads for decades. Instead of invoking invisible particles, MUND tweaks the equations of gravity just slightly, suggesting that on the scale of galaxies, Newton's laws need an update. The idea took shape in the 1980s when physicist Mordechai Milgrom noticed something peculiar. The rotation curves of galaxies, those telltale signs of missing mass, could be explained not by hidden matter, but by a tiny adjustment to how gravity behaves at extremely low accelerations. In this view, the outer stars in galaxies aren't being held in place by dark matter's pull. They're simply responding to a modified force of gravity, one that grows stronger than expected as you move farther from a galaxy's core. At first glance, MUND's elegance is undeniable. It explains galactic rotation without requiring vast halos of invisible stuff. It matches observations of hundreds of galaxies with startling precision, often better than some dark matter models. And it does all this without introducing hypothetical particles we've never detected. But here's the catch: while MUND excels at predicting how individual galaxies rotate, it struggles to explain other cosmic phenomena where dark matter thrives. Take galaxy clusters, the titanic assemblies of hundreds of galaxies where the visible matter alone can't account for their immense gravitational pull, even with MUND adjustments. Or the way dark matter's gravitational fingerprints appear in the bending of light around massive objects, a phenomenon MUND can't fully replicate. Then there's the bullet cluster, one of the most striking pieces of evidence for dark matter's existence. When two galaxy clusters collided, their visible gas slowed and heated up, but their gravity, tracked by lensing effects, kept moving ahead, as if most of the mass had passed right through the collision like a ghost. MUND struggles to explain this separation of mass from visible matter, while dark matter models handle it with eerie precision. The debate isn't settled. Some researchers propose hybrid theories, blending elements of modified gravity with a sprinkle of dark matter. Others argue we haven't yet uncovered the full potential of MUND's underlying principles. But for now, most physicists lean toward dark matter, not just because of its explanatory power, but because it fits snugly into our larger cosmic puzzle, from the way galaxies form to the very structure of the universe itself. So where does that leave us, staring down two cosmic mysteries instead of one? Either the universe is filled with an invisible substance we've yet to detect, or our foundational understanding of gravity is fundamentally incomplete. Both possibilities are humbling, both rewrite the rules, and both remind us that the cosmos still holds secrets we've only begun to scratch. If dark matter is the invisible hand shaping the cosmos, then most scientists believe it must be cold, slow-moving and heavy, like a cosmic anchor quietly steering the formation of galaxies. This is the heart of the cold dark matter theory, the leading explanation for how our universe's large-scale structure emerged from the primordial soup of the Big Bang. Picture throwing a handful of gravel into a still pond. The heaviest stones sink fastest, creating ripples that guide the smaller pebbles into place. Cold dark matter would work the same way, its sluggish particles clumping early on, carving out gravitational wells that normal matter, stars, gas, and dust later tumbled into. But this elegant idea hits a snag when we look at the tiniest galaxies. According to supercomputer simulations, cold dark matter should have littered the universe with thousands of dwarf galaxies, orbiting larger ones like fireflies around a lantern. Instead, we've found only a handful. This is the missing satellites problem, a glaring mismatch between prediction and reality that's kept astrophysicists awake for decades. The numbers just don't add up. Our cosmic neighborhood should be swarming with these faint, small galaxies, but the sky tells a different story. One possible fix. Maybe we're just not seeing them. Dwarf galaxies are notoriously dim, often cloaked in clouds of gas or stripped apart by their larger neighbors. Telescopes might be missing them, like trying to spot a candle flickering behind a foggy window. Yet, even after scouring the skies with ultra-sensitive instruments, the tally remains stubbornly low. Another explanation suggests cold dark matter might not be quite as cold as we thought. If these particles had even a tiny amount of heat wiggling ever so slightly, they'd resist clumping at the smallest scales, leaving fewer dwarf galaxies in their wake. Yet the plot thickens. Some of the dwarf galaxies we have found don't behave as expected. Their stars move in bizarrely synchronized orbits, as if trapped in some unseen cosmic dance, while others seem to orbit in flat planes around their host galaxies, defying the chaotic jumble predicted by simulations. It's as if the universe is teasing us, offering clues that don't quite fit the cold dark matter puzzle. So where does that leave the theory, still standing but on shakier ground? Cold dark matter remains the best tool we have to explain the universe's grand structure, from galaxy clusters to the cosmic web itself. But these stubborn little galaxies, or the lack thereof, are a reminder that the cosmos loves to defy our tidy explanations. Whether the answer lies in tweaking the theory, inventing new detection methods, or rewriting the rules entirely, one thing's clear: the shadows hiding in the cosmic deep are far more mischievous than we imagined. If dark matter is real, then what exactly is it made of? The leading candidate hides behind a name that sounds like it's straight out of a sci-fi novel: WIMP, or weakly interacting massive particles. These hypothetical particles are thought to be heavy, sluggish, and nearly ghostly, barely interacting with normal matter except through gravity. Picture trying to catch smoke with your bare hands. That's the level of frustration scientists face when hunting for WIMP. Despite decades of effort, not a single one has been caught in the act. The logic behind WIMP is compelling. They fit neatly into something called the WIMP miracle, a cosmic coincidence where particles with just the right mass and weak interactions would naturally emerge from the early universe in the exact amounts we need to explain dark matter's gravitational effects. It's as if the universe whispered a hint in physicists' ears, a solution so elegant it had to be true. And yet, after burying detectors deep underground to shield them from cosmic noise, after years of waiting for even the faintest flicker of a WIMP collision, the detectors remain silent. But WIMP aren't the only suspects. Another contender, the Action, is the opposite in almost every way: tiny, lightweight, and more like a cosmic whisper than a heavyweight shadow. Actions were originally dreamed up to solve a completely unrelated puzzle in particle physics, but they just so happen to have the perfect properties to be dark matter. Unlike WIMP, actions wouldn't bump into atoms. Instead, they'd reveal themselves by subtly altering the behavior of magnetic fields, or even transforming into photons under the right conditions. Teams around the world are now tuning ultra-sensitive instruments, hoping to catch an action's faint signal like a radio picking up a station from across the universe. Then there's the possibility we've been looking in entirely the wrong place. Some theories propose dark matter isn't a single particle but a hidden ecosystem, a dark sector, with its own forces, particles, and even dark atoms. Imagine an entire shadow universe existing alongside ours, completely invisible, barely touching our reality except through gravity. It's a wild idea, but when the evidence refuses to line up, scientists have to entertain the extraordinary. So why haven't we found anything yet? It could be that dark matter particles are even more elusive than we thought, interacting so rarely that our detectors might as well be trying to net a breeze. Or perhaps they're just beyond our current technology, hiding in energy ranges or scales we can't yet probe. Some researchers wonder if dark matter isn't particle-like at all, but something stranger, primordial black holes from the dawn of time, or even flaws in the fabric of space-time itself. The silence isn't just a setback, it's a tantalizing clue. Every null result forces us to rethink, to dig deeper, to question assumptions we didn't even realize we'd made. If dark matter is out there, it's playing a masterful game of hide and seek, revealing just enough to keep us searching but never enough to let us win. And that's the heart of this mystery. The more we chase it, the more it reshapes our understanding of what matter, or even reality, could be. Imagine a signal so persistent it's been pulsing for over 2 decades, yet so elusive that no one can agree if it's real or a cosmic mirage. That's the enigma of the DAMA/LIBRA experiment, one of the most hotly debated mysteries in the hunt for dark matter. Deep beneath Italy's Gran Sasso mountain, shielded from cosmic rays by nearly a mile of rock, a detector filled with sodium iodide crystals has been picking up a peculiar rhythm, a faint but regular flicker that peaks every June and dips every December. The team behind DAMA claims this is the smoking gun for dark matter, a telltale sign of WIMP streaming through Earth as our planet moves through the galaxy's halo. Here's why it's so controversial. If dark matter fills the Milky Way, Earth should plow through it faster in June when our orbit adds to the galaxy's motion, creating a detectable wind of particles. By December, we'd be moving against the current, reducing the signal. That's exactly the pattern DAMA reports, an annual modulation so precise it aligns perfectly with dark matter's expected behavior. The problem, no other experiment has seen it. Take the LUX detector in South Dakota, buried even deeper underground, or xenon in Italy, both designed to catch WIMP with ultra-sensitive liquid xenon. They've found nothing, not a trace. Scientists have scrutinized every possible explanation: background radiation, seasonal temperature shifts, even subtle quirks in DAMA crystal detectors. Some suggest mundane causes, like cosmic rays interacting differently with Earth's atmosphere as it tilts through the year. Others propose exotic physics, like dark matter behaving in ways we haven't modeled. Then there's the sodium iodide itself. Unlike xenon, these crystals might interact with dark matter in unexpected ways, amplifying signals other detectors miss. Or perhaps the WIMP DAMA claims to see are lighter or more peculiar than standard models predict, slipping past other experiments designed for heavier particles. It's like tuning a radio to the wrong frequency. You might miss the broadcast entirely, even if it's playing right beside you. The debate rages on because DAMA data is statistically robust. 20 years of consistent signals aren't easily dismissed as noise. Yet science demands reproducibility, and until another detector catches the same whisper in the dark, the mystery remains. Future experiments like COSIGN, using identical materials to DAMA, aim to settle the score. Until then, this tantalizing signal lingers in limbo, a ghost in the machine, neither confirmed nor debunked, keeping the door cracked open for a discovery that could rewrite the rules, or reveal just how clever nature is at leading us astray. Sometimes the universe hands us a gift, an event so striking it cuts through decades of debate like a spotlight. The bullet cluster is one of those gifts, a pair of galaxy clusters that collided at unimaginable speeds, leaving behind a cosmic crime scene where dark matter's fingerprints are smeared across the sky. Here's what makes it so extraordinary. When these titanic structures smash together, their gas, the hot, glowing plasma that makes up most of a cluster's visible mass, piled up in the center, slowed by friction like two clouds merging in a storm. But something else kept racing ahead, something invisible. By mapping the distortion of background galaxies through gravitational lensing, scientists traced the cluster's true mass and found it wasn't where the gas was. It had sailed right through the collision as if it weren't there at all. This is the bulletproof case for dark matter. If the missing mass were just a quirk of gravity, as Mund suggests, the lensing effect would have followed the gas. Instead, the mass and the gas divorced mid-collision, proving that most of what holds these clusters together doesn't interact with light, doesn't slow down, doesn't even notice ordinary matter. It's like watching two crowds pass through each other in a plaza. Only one group leaves footprints while the other moves silently, leaving no trace except the eerie sensation of being brushed by something unseen. But the bullet cluster isn't just evidence, it's a puzzle box. The separation between dark and visible matter isn't perfect. Some of the dark mass did lag behind, hinting that maybe, just maybe, it isn't entirely ghostly. Could dark matter particles occasionally bump into each other, creating faint drag? Or does the cluster hide subtler structures like dark matter subhalos that got tangled in the wreckage? The more we stare, the more questions arise. Even this gold standard proof comes with asterisks, reminding us that dark matter, if it's real, is far stranger than we've imagined. And then there's the kicker: the bullet cluster isn't alone. Other mergers like MAX J0025.7-1222 show similar splits between mass and light. Each one is a controlled experiment, a natural laboratory where the universe tests our theories without mercy. If dark matter were a mirage, these collisions would have shattered the illusion. Instead, they've turned skepticism into consensus for many, because when you see the same shadow play out again and again across billions of light years, it's hard to call it coincidence. Yet for all its power, the bullet cluster raises a haunting question. How many other cosmic collisions have we missed? How many bulletins from the dark universe slipped past us unnoticed because we didn't have the tools or the luck to catch them? It's a reminder that the cosmos doesn't hand us answers. It scatters clues, and it's up to us to piece them together before the light fades. Gravity is the architect of the cosmos, but in the early universe it had a silent partner, dark matter. Without this unseen scaffolding, galaxies as we know them might never have taken shape. Picture the universe a few 100 million years after the Big Bang, a swirling sea of gas too thin and scattered to collapse under its own weight. Ordinary matter alone couldn't pull itself together fast enough to form the vast structures we see today. But dark matter changed the game. Its gravity acted like a cosmic magnet, drawing gas into dense pockets where stars and galaxies could ignite. Here's the twist: dark matter didn't just help, it dominated. While normal matter was busy bouncing off photons in the hot early universe, dark matter, unaffected by light, quietly clumped together, forming invisible wells of gravity. Gas followed these contours like water flowing into valleys, condensing into the first proto-galaxies. Simulations show this process unfolding with startling speed. Dark matter's pull accelerated galaxy formation so dramatically that some stars may have lit up when the universe was less than 2% of its current age. But the story isn't just about speed. Dark matter also dictated the shape of galaxies. Spiral galaxies like the Milky Way owe their graceful arms to the gravitational embrace of their dark halos, which stabilized rotating disks of gas and stars. Without that invisible anchor, galaxies would spin themselves apart, their stars scattering like marbles on a tilted table. Even more striking are the dwarf galaxies, tiny and dim, which cling to the outskirts of larger ones like cosmic satellites. These faint survivors are thought to be remnants of the first dark matter clumps, too small to attract much gas but stubbornly persistent, orbiting their hosts for billions of years. Yet mysteries linger. Some of the earliest galaxies observed by telescopes like JWST are too massive, too structured for their age, defying predictions about how quickly dark matter could have assembled them. Could dark matter interact with itself in ways we haven't accounted for, clumping faster than expected? Or does this mismatch hint at deeper flaws in our models? The answers lie buried in the faint glow of those ancient stars, waiting for the next breakthrough to pull them into the light. One thing's certain: dark matter didn't just set the stage for galaxies, it wrote the script. From the grandest spirals to the tiniest dwarfs, its gravitational touch is etched into every corner of the cosmic web. And as we peer deeper into the past, we're not just tracing the history of stars and gas. We're decoding the diary of the unseen. There's a glaring mismatch in our cosmic simulations: dark matter halos so massive they should be crowned with blazing galaxies. Yet when we point our telescopes at their predicted locations, we find nothing but empty space. This is the too big to fail problem, a paradox that's been gnawing at astrophysicists for years. According to our best models, the universe should be littered with these colossal halos, each one a gravitational powerhouse capable of anchoring a bright, star-filled galaxy. But the reality, they're ghost towns. The issue first came to light when supercomputer simulations, tracking dark matter's behavior from the Big Bang to today, revealed a startling pattern. Certain halos grew to staggering sizes, some as hefty as the Milky Way's own dark matter envelope. Yet when astronomers scanned the skies, these behemoths were conspicuously dark. No swirling gas, no glittering stars, just voids where bustling galaxies ought to be. It's like stumbling upon the foundations of a metropolis in the desert, complete with roads and power lines, but no buildings or people. One leading theory blames reionization, a cosmic upheaval that occurred a few 100 million years after the Big Bang. As the first stars ignited, their ultraviolet radiation flooded the universe, heating intergalactic gas to extreme temperatures. In smaller halos, this superheated gas might have escaped gravity's grip, starved of the raw materials needed to form stars. But the too big to fail halos are different. They're too massive for reionization to explain away. Their gravity should have easily held onto gas, making their emptiness even more puzzling. Another possibility hinges on dark matter's own quirks. If it's not perfectly cold but slightly warm, with particles moving just fast enough to resist clumping at the smallest scales, that could prevent gas from cooling and condensing in these halos. Yet even this elegant fix doesn't fully account for the scale of the discrepancy. Some halos are missing galaxies they should have had no trouble holding onto, suggesting forces we haven't yet imagined might be at play. Then there's the wild card, feedback from supermassive black holes. In some galaxies, these monsters blast out enough energy to strip away star-forming gas entirely. Could similar outbursts have sterilized the too-big-to-fail halos early on, leaving them permanently dark? It's a tantalizing idea, but without proof that black holes were active in these voids, it remains speculative. What makes this mystery so gripping isn't just the gap between theory and observation, it's the stakes. If our simulations can't predict where galaxies don't form, how much can we really trust them to explain where they do? Every empty halo is a silent rebuke, a reminder that dark matter's story is far from written. And until we solve this riddle, we're left staring at the shadows, wondering what else the universe has forgotten to tell us. Stretching across billions of light years like threads in a spider's web, the cosmic filaments of dark matter form the hidden highways of the universe. These colossal tendrils, some spanning half the observable cosmos, connect galaxy clusters in a delicate, intricate dance, channeling matter and energy across unimaginable distances. Picture standing in a forest at night, seeing only the fireflies dotting the trees while the branches linking them remain invisible. That's how dark matter filaments work. We spot the glowing galaxies at their intersections, but the web itself hides in plain sight. How do we know it's there? The answer lies in the eerie uniformity of the cosmic web. When astronomers mapped millions of galaxies, they didn't find them scattered randomly. Instead, they clustered along precise, intersecting lines, as if drawn by some unseen hand. These patterns matched supercomputer simulations of dark matter's gravitational influence, where slight density fluctuations in the early universe grew into vast filaments over billions of years. Ordinary matter, the gas and dust that became stars, simply flowed into these pre-marked channels, like rainwater tracing the grooves of a leaf. Yet filaments aren't just passive scaffolding. They're cosmic accelerators, funneling gas into galaxy clusters at their nodes at speeds approaching thousands of kilometers per second. This incoming torrent fuels star formation, triggers galactic collisions, and even shapes the fate of entire clusters. In the Coma supercluster, for example, galaxies stream along dark matter filaments like commuters on a subway line, destined to merge in a slow-motion pileup over cosmic time. But here's the twist: not all filaments are created equal. Some are dense and prominent, like the cosmic reef linking the Pisces-Cetus supercluster, while others are wispy and faint. Their strength depends on the dark matter density they formed from, with the thickest filaments tracing back to the most pronounced ripples in the early universe. The differences don't stop there. Recent observations suggest filaments might contain their own faint glow, not from stars but from scattered intergalactic plasma, energized by the motion of dark matter's gravity. The most astonishing clue comes from gravitational lensing. When light from distant quasars passes through a filament, its path bends slightly, revealing the filament's mass like a watermark on cosmic paper. Some of these structures weigh as much as a small galaxy cluster, yet remain virtually transparent, their dark matter content outweighing visible matter by a factor of 10. It's staggering to think these ghostly rivers could dictate the flow of entire superclusters while barely leaving a trace. What's next? Telescopes like Euclid and the upcoming Nancy Grace Roman Space Telescope aim to map these filaments in unprecedented detail, hunting for the faint distortions they imprint on passing light. Each new observation peels back another layer of the mystery, showing us a universe far more connected and far stranger than we ever imagined. Because if dark matter's web is real, then every galaxy we see is just a stop along a hidden highway system, with routes charted long before the first star was born. One of the most heated debates in modern cosmology isn't just about dark matter. It's about the speed of the universe itself. For over a decade, astronomers have been locked in a standoff over the Hubble constant, the number that describes how fast the cosmos is expanding. On one side, measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest a relatively sedate expansion rate. On the other, observations of nearby supernovas and pulsating stars reveal a universe stretching faster than the early relic predicts. The gap between these values isn't just a rounding error, it's a full-blown crisis dubbed the Hubble tension, and it hints that something fundamental is missing from our understanding of cosmic history. This is where dark matter enters the fray. If dark matter behaves differently than we've assumed, if it interacts with itself, decays over time, or even morphs into another form, it could tweak the universe's expansion in ways that resolve the discrepancy. Picture a clock running slightly too fast. You could fix it by adjusting the gears, or you might discover an entirely new mechanism inside, one you never knew existed. Dark matter could be that hidden mechanism, subtly altering how gravity sculpted the early universe and leaving traces in today's conflicting measurements. One provocative idea suggests dark matter might not be completely stable. What if a fraction of it decayed into radiation or other particles billions of years ago? This extra burst of energy would have gently pushed the universe apart, speeding up expansion just enough to align with modern observations. Alternatively, if dark matter interacts with itself through some unknown force, colliding or repelling like charged particles, it could have changed how structures formed in the cosmos's youth, indirectly affecting the Hubble constant we measure today. Then there's the dark energy wildcard. Most models treat dark energy as a constant force, but what if it's not? If dark energy's strength has fluctuated over time, perhaps boosted by interactions with dark matter, it could explain why the early and late universe seem to disagree on expansion rates. Imagine blowing up a balloon in fits and starts, sometimes fast, sometimes slow. The inconsistency wouldn't just affect the balloon's current size, it would rewrite the entire story of how it inflated. The stakes couldn't be higher. If the Hubble tension points to new physics in the dark sector, it would upend decades of assumptions, forcing us to rethink everything from galaxy formation to the ultimate fate of the cosmos. But here's the catch. Every proposed tweak to dark matter must also explain why it hasn't shown up in other experiments, from particle colliders to underground detectors. The solution, if it exists, has to be sneaky, just influential enough to bend the universe's expansion, yet invisible enough to evade every other test we throw at it. For now, the tension remains, a nagging reminder that even our best theories are provisional. Whether the answer lies in dark matter's secrets, dark energy's quirks, or something even stranger, one thing is clear: the universe is still holding back its most astonishing revelations. If dark matter particles are their own antimatter counterparts colliding and annihilating in bursts of energy, we should be drowning in gamma rays. That's the expectation that's driven decades of searches, from mountaintop observatories to space telescopes scanning the skies for faint, telltale glows. Yet the universe remains stubbornly quiet, leaving scientists to grapple with a paradox. Why haven't we seen even a whisper of dark matter annihilating, especially in places where it's densest? Take the Milky Way's core, for instance. Packed with dark matter, it should be a fireworks display of gamma radiation, the signature of particles smashing together at incredible speeds. Fermi-LT, a space telescope designed to catch these signals, has stared at the galactic center for years, and while it's detected some excess gamma rays, the signal is messy, ambiguous, easily explained by mundane sources like pulsars or cosmic rays. It's like listening for a symphony in a crowded marketplace. You might catch a note or two, but the roar of background noise drowns out the melody. Then there's the dwarf galaxy problem. These tiny, dim satellites orbiting the Milky Way are thought to be nearly pure dark matter, with very few stars to muddy the signal. If annihilation is happening anywhere, it should be unmistakable here. But again, nothing conclusive. The gamma rays we do detect could just as easily come from distant quasars or other astrophysical phenomena. the silence is deafening, and for theorists it's a growing headache. One possibility: dark matter annihilates far more sluggishly than we've assumed. Maybe the particles interact so weakly that even in dense regions, collisions are rare, like two bullets fired across a continent somehow finding each other midair. Or perhaps the annihilation products aren't gamma rays at all, but something more exotic: neutrinos or even invisible particles we've yet to discover. Then there's the nuclear option. What if dark matter doesn't annihilate? Maybe it's not its own antimatter twin, or maybe the process requires conditions so extreme they only occur in places we haven't thought to look. Some researchers speculate that primordial black holes, leftover knots of spacetime from the Big Bang, could be soaking up annihilation signals before they reach us, swallowing the evidence whole. The deeper we dig, the stranger the possibilities become. If annihilation isn't the answer, then what is dark matter doing in those crowded galactic cores? Just sitting there silently without a single collision. It defies intuition, yet the data refuses to bend. Every null result forces us to reconsider, to peel back another layer of assumptions. Because if there's one thing the cosmos loves, it's proving us wrong, then daring us to try again. Our galaxy isn't just a glittering spiral of stars, it's cloaked in an enormous, invisible shroud of dark matter, stretching far beyond the Milky Way's luminous edge. This halo, 10 times more massive than all the stars and gas combined, is what keeps our galaxy from flying apart. Yet for something so fundamental, it's full of puzzling contradictions. Simulations predict halos should have a specific density profile, smooth and concentrated toward the center, like syrup pooling at the bottom of a bowl. But when astronomers map the Milky Way's dark matter by tracking the motions of distant stars, the reality isn't so neat. Some regions appear lumpy, as if the halo is clumped into invisible islands, while others stretch thinner than expected, like a ghostly fog refusing to settle. The mystery deepens when we look at our galaxy's shape. Most simulations suggest dark matter halos should be slightly flattened, like a squashed beach ball, due to the Milky Way's rotation. But recent studies of hypervelocity stars, objects flung outward by the supermassive black hole at our galactic center, suggest something stranger. Their trajectories hint that the halo might be lopsided, denser on one side than the other, almost as if a colossal, unseen collision knocked it off kilter billions of years ago. If true, it would mean our galaxy's dark matter isn't just a passive backdrop but a dynamic structure, still bearing scars from ancient cosmic violence. Then there's the problem of the Milky Way's missing satellites. Cold dark matter models predict our halo should be swarming with hundreds of dwarf galaxies, each anchored to its own clump of dark matter. Instead, we've found barely a few dozen, and their orbits don't always match expectations. Some move in bizarrely synchronized planes, like flies trapped in an unseen web, while others seem to avoid the halo's densest regions entirely. It's as if the dark matter isn't distributed the way our simulations insist it should be, or worse, that we're fundamentally misunderstanding how it behaves on galactic scales. One possible explanation lies in feedback from the Milky Way's own stars. Supernova and stellar winds might have blown gas out of smaller halos, starving them of the material needed to form visible galaxies. But that doesn't fully account for the halo's odd density fluctuations or its apparent asymmetry. Another theory suggests dark matter isn't perfectly cold but slightly warm, its particles jostling just enough to resist clumping at the smallest scales. Yet even this tweak struggles to explain why the Milky Way's halo seems so messy compared to the pristine halos in our simulations. The most tantalizing clue comes from Gaia, the space telescope mapping 1 billion stars with pinpoint precision. By tracing the paths of globular clusters and streams of stars ripped from cannibalized galaxies, Gaia has revealed subtle wrinkles in the halo's gravity ripples that might be the fingerprints of past mergers. Perhaps the Milky Way's dark matter isn't one smooth halo but a patchwork of smaller ones, layered together like strands in a cosmic rope. Each time our galaxy swallowed a dwarf neighbor, its dark matter could have tangled into ours, leaving behind a knotted, uneven structure that no simulation yet can replicate. What's clear is this: the Milky Way's dark matter halo isn't just a static shell. It's a living archive of our galaxy's violent history, shaped by collisions, tides, and forces we've only begun to guess at. And until we untangle its secrets, we're left with a sobering thought: the very thing holding our galaxy together might also be the thing we understand least. We've always assumed dark matter is a cosmic loner barely interacting with anything, even itself. But what if it's not? What if dark matter has its own hidden quantum world, buzzing with invisible forces and particles we can't detect? This isn't just idle speculation. Some theories suggest dark matter might interact through its own version of electromagnetism, mediated by hypothetical particles called dark photons. Picture this: an entire shadow universe where dark matter particles repel or attract each other through unseen fields, creating structures and behaviors we've never imagined. The idea of dark photons is especially tantalizing. Just as ordinary photons carry the electromagnetic force between charged particles, dark photons could transmit force between dark matter particles, allowing them to push, pull, or even collide in ways that leave no trace in our visible universe. This could explain strange anomalies, like why some galaxies seem to have smoother dark matter distributions than expected, as if an unseen force was buffering their collisions, preventing the clumpiness we'd anticipate. Then there's the possibility of quantum entanglement on a cosmic scale. If dark matter particles can become entangled, changes to one could instantly affect another, regardless of distance. It's a wild concept, but entanglement is already a proven phenomenon in our quantum world. Why couldn't the dark sector have its own version? This could create bizarre large-scale correlations in the cosmos, invisible threads tying distant galaxies together in ways we can't yet measure. The challenge, of course, is proving any of this. If dark forces only act within the dark sector, how do we detect them? One clue might come from subtle distortions in the cosmic microwave background, the afterglow of the Big Bang. If dark photons exchanged energy in the early universe, they could have left faint imprints in this ancient light. Another approach involves ultra-sensitive experiments on Earth, like the search for dark electromagnetism, are tiny, unexpected forces that might tug on ordinary matter in ways standard physics can't explain. But the most mind-bending possibility: dark matter might not be one thing but many, a whole ecosystem of particles and forces as rich and complex as our own visible universe. There could be dark atoms, dark chemistry, even dark stars shining with dark light. We'd never see them, but their gravity would still shape the cosmos. It's a humbling thought. After centuries of mapping the heavens, we might have missed half the story, simply because it was written in ink we couldn't see. Until we find a way to peer into this hidden quantum realm, these ideas remain at the edge of science, where the most thrilling mysteries often lie. But if even one of them is true, it would rewrite not just the story of dark matter, but the very laws we thought governed reality. Deep beneath the Milky Way's glittering spiral arms, hidden from even our most powerful telescopes, a shadowy structure might lurk, one that could rewrite Earth's history. This is the dark disk hypothesis, a provocative idea suggesting our galaxy contains a dense, pancake-shaped layer of dark matter, separate from its spherical halo, orbiting in sync with the visible stars. If real, this disk wouldn't just be a curiosity. Some scientists argue it could be a silent killer, responsible for periodic cataclysms that have scarred our planet. The theory hinges on a simple but unnerving premise. As our solar system bobs up and down through the Milky Way's plane during its 250 million-year orbit, it could periodically plunge through this dark disk. Each pass would expose Earth to a surge of gravitational disturbances enough to nudge comets from the icy outskirts of the solar system, sending them hurtling toward the inner planets. The timing is suspiciously convenient. These crossings happen roughly every 30 million years, eerily matching the interval between some of Earth's most devastating mass extinctions, like the dinosaur-killing asteroid 66 million years ago. But how would a dark disk form in the first place? Simulations suggest it could be a fossil of the Milky Way's violent youth. When our galaxy cannibalized smaller ones, their dark matter, unaffected by the friction that slows visible gas, might have settled into the plane over time like flour sifting to the bottom of a jar. Alternatively, interactions between dark matter particles could have siphoned away energy, causing them to collapse into a disk. The result, a stealthy, high-density layer, invisible but with gravity strong enough to wreak havoc. Not everyone's convinced. Critics point out that if a dark disk exists, its gravitational tug should subtly alter the orbits of stars near the galactic plane, yet precise measurements from missions like Gaia show no obvious distortions. Others argue that comet showers could be triggered by other cosmic rhythms, like the solar system's oscillation through the Milky Way's crowded midplane, where molecular clouds and stellar clusters lurk. But the dark disk's proponents counter that ordinary matter alone can't fully explain the timing or intensity of these extinction cycles. The hunt for answers is heating up. New telescopes are scouring the Milky Way's outskirts for faint, fast-moving stars whose trajectories might betray the disk's presence. Meanwhile, physicists are re-examining dark matter's potential interactions, asking whether certain particle types could preferentially sink into disks. If they're right, the implications are staggering. Earth's history, its rise and fall of species might not just be shaped by random asteroids or volcanic eruptions, but by an invisible cosmic pendulum ticking away in the dark. The chilling takeaway, our planet's fate could be tied to something we'll never see, a reminder that even in our own galactic backyard, the universe keeps its most dangerous secrets hidden in plain sight. What if dark matter isn't made of exotic particles at all, but of black holes so ancient they predate the stars themselves? This is the audacious idea behind primordial black holes, hypothetical relics from the universe's first chaotic moments that could silently make up the bulk of missing mass. Born in the extreme density fluctuations of the early cosmos, these black holes wouldn't form from collapsing stars like their modern counterparts. Instead, they'd be fossils of the Big Bang, scattered across space like invisible landmines, their gravity the only clue to their presence. The theory isn't new. In the 1970s, Stephen Hawking and others toyed with the notion that tiny black holes, some no heavier than an asteroid, others as massive as 1,000 suns, could have condensed from the seething plasma of the infant universe. If they existed in just the right numbers, their combined gravity might explain dark matter's elusive pull. No need for WIMP or actions. The answer would be lurking in the shadows of Einstein's equations all along. But here's where things get thorny. Primordial black holes face a Goldilocks problem. They can't be too big or too small, only just right. Too massive, and their gravity would distort the light from distant quasars in ways we don't observe. Too light, and they'd have evaporated by now, thanks to Hawking radiation, a process where black holes slowly leak energy and vanish. The sweet spot between 100 quadrillion grams and a few lunar masses, a range where they'd still be around today without leaving obvious scars on the cosmos. Even then, the evidence is shaky. When LIGO detected gravitational waves from colliding black holes in 2015, some researchers perked up. Could these mergers involve primordial black holes? Possibly, but the events are too rare to account for all of dark matter. Worse, meticulous surveys like OGLE, which monitors millions of stars for subtle flickers caused by unseen objects passing in front of them, have largely drawn a blank. If primordial black holes were common, they'd occasionally drift between us and distant stars, bending their light in telltale microlensing events. yet the observed rates are far too low to explain dark matter's abundance. Then there's the cosmic structure hurdle. Dark matter's fingerprints are everywhere in the way galaxies rotate, how clusters collide, even in the delicate web of filaments connecting the universe. Primordial black holes, being compact and point-like, struggle to replicate these effects without disrupting other observations. Their gravity would clump differently than diffuse particle dark matter, potentially leaving gaps in the cosmic web or shredding dwarf galaxies that seem intact. But don't count them out just yet. A tantalizing loophole remains. What if these black holes aren't alone? Some theories suggest they could be surrounded by halos of dark matter particles, creating hybrid objects that blend both ideas. Others propose they formed in clusters, avoiding microlensing limits by rarely wandering solo across our line of sight, the most thrilling possibility. We might have already spotted them. The mysterious Planet 9, a hypothetical world tugging at objects in the outer solar system, could instead be a primordial black hole no larger than a grapefruit hiding in our cosmic backyard. Future missions could hunt for its telltale gamma-ray glow or the sparks it'd produce when swallowing stray comets. Whether primordial black holes are dark matter's missing piece or just another cosmic red herring, their allure is undeniable. They force us to question not just what dark matter is, but how creatively the universe might hide its secrets. After all, if the answer has been lurking in black holes all along, it'd be the ultimate cosmic irony, the darkest objects solving the darkest mystery. Before the first stars flickered to life, before galaxies spun into being, the universe was a silent sea of darkness, and dark matter may have been the unseen midwife that guided its birth. The cosmic dawn, that pivotal era when the first stars ignited, didn't just happen randomly. It was orchestrated by the gravitational pull of dark matter, which sculpted the primordial gas into dense enough clumps to trigger nuclear fusion. Without it, the universe might have remained a featureless void, endlessly stretching without a single spark to light the way. But dark matter's role wasn't just about getting the party started. It may have also dictated the tempo. The timing of reionization, the process where ultraviolet radiation from those first stars tore apart the hydrogen fog filling the early universe, is one of cosmology's biggest puzzles. Observations from telescopes like JWST reveal galaxies shining far earlier than expected, suggesting reionization occurred in fits and bursts rather than a smooth transition. Could dark matter be the reason? Here's one possibility. If dark matter wasn't entirely cold but slightly warm, with particles moving just fast enough to resist clumping at the smallest scales, it could have delayed the formation of the tiniest galaxies. That would leave fewer but more massive stars to flood the cosmos with UV radiation, creating patchy regions of ionized gas instead of a uniform glow. Alternatively, if dark matter interacted with itself colliding or radiating energy, it might have funneled gas into unusual configurations, birthing supercharged stars that burned brighter and died younger, spewing radiation at rates that shocked the infant universe awake. Then there's the wild card of dark matter annihilation. If particles occasionally collided and released energy in the early cosmos, those bursts could have heated the gas, either stalling star formation in some regions or supercharging it in others. Picture a cosmic seesaw. In one patch, dark matter's heat keeps gas too diffused to collapse, while in another, its gravity compresses gas into uber stars that flood their surroundings with ionizing light. The result, a reionization process as uneven as a storm-lashed sea, with islands of clarity amid vast stretches of lingering fog. The implications are staggering. If dark matter shaped reionization, it didn't just influence when stars formed, it altered the very blueprint for how galaxies grew. Those early bursts of radiation carved bubbles in the hydrogen haze, creating pathways for light to travel and setting the stage for everything that followed. Without dark matter's invisible hand, the universe might have remained shrouded longer, its galaxies smaller, its stars dimmer. Yet for all its power, dark matter's early influence remains frustratingly opaque. JWST glimpses of shockingly mature galaxies in the universe's infancy have only deepened the mystery. If dark matter is the key, it's one we're still learning how to turn. Each new observation peels back another layer, revealing a cosmic dawn far more complex and far more strange than we ever dreamed. Right now, as you watch this, our solar system is barreling through a cosmic anomaly. A rogue river of dark matter streaming through the Milky Way at nearly 500 kilometers per second. Scientists call it the S1 stream, but it's earned a more dramatic nickname, the dark matter hurricane. Unlike anything else in our galaxy, this high-speed current isn't made of stars or gas. It's the shattered remnants of a dwarf galaxy devoured by the Milky Way billions of years ago, its stars long since scattered, leaving only the ghostly wake of its dark matter behind. Here's what makes it so extraordinary. Most dark matter in our galaxy moves in a stately, predictable halo, orbiting the center like bees around a hive. But the S1 stream is different, a concentrated torrent cutting against the flow, a cosmic undercurrent racing almost perpendicular to the Milky Way's rotation. When it was discovered in 2017, thanks to the Gaia spacecraft's precise mapping of stellar motions, researchers realized something startling: our solar system is inside it. Right now, and that changes everything for dark matter hunters. This isn't just a curiosity, it's a golden opportunity. Normally, experiments like Xenon or LUX have to sift through endless noise, hoping to catch the faintest whisper of a dark matter particle colliding with ordinary matter. But the S1 stream offers a rare advantage. Its dark matter isn't just drifting lazily, it's screaming toward us, meaning the particle should hit detectors with higher energy, leaving slightly stronger signals. It's the difference between trying to hear a pin drop in a silent room and hearing one clink during a passing parade. Yet there's a catch: the S1 stream isn't uniform. Simulations suggest it's a tangled braid of substreams, each with slightly different densities and trajectories. That means the dark matter, wind buffeting Earth, might gust and wane over time, creating a signal that's frustratingly inconsistent. Some models even predict temporary surges, moments when the density spikes enough to give detectors a fighting chance. The key is timing. If experiments can synchronize their searches with these predicted peaks, they might finally snag definitive proof. But the implications go beyond detection. If dark matter interacts with itself even weakly, the S1 stream's structure could reveal clues. Imagine tossing dye into a river. How it swirls and spreads tells you about the water's flow. Similarly, distortions in the stream's shape might hint at dark matter's hidden forces. Does it clump more than expected? Are there gaps suggesting particle collisions? Every anomaly is a breadcrumb leading back to dark matter's true nature. Then there's the existential question: could this invisible hurricane affect us? The answer is almost certainly no. Dark matter's ghostly nature means it sails through Earth like we're not even here. But on cosmic timescales, its gravity might leave subtle marks. Some theorists speculate that past encounters with similar streams could have nudged comets from the Oort cloud, sending icy projectiles toward the inner solar system. It's a long shot, but if true, dark matter might have indirectly shaped life's trajectory on Earth by meddling with our planet's bombardment history. For now, the S1 stream remains a tantalizing what if. No experiment has yet claimed a detection tied to it, and some researchers caution that its density might be too low to matter. But one thing's certain: the universe has handed us a gift, a high-speed, high-stakes test of our darkest theories. All we have to do is reach out and catch it. What if dark matter isn't just hidden in space, but in time itself? This mind-bending possibility suggests that dark matter's elusive nature might not just be about where it is, but when it is. Imagine standing on a shoreline, watching waves crash at your feet while somewhere far out at sea, a storm is brewing. You can't see the storm yet, but its effects, the distant swells, are already shaping the water around you. Dark matter might be something like that, a cosmic force not just operating in our three-dimensional reality, but leaking into our universe from extra dimensions or even moving through time at a different rate. The idea stems from one of the most perplexing quirks of dark matter. Its gravitational pull appears everywhere, yet it refuses to interact with light, matter, or even itself in any way we can detect. If it was simply an exotic particle, we'd expect at least some trace of collisions or decays by now. But what if that's the wrong way to look at it? Some theoretical models suggest dark matter could be a shadow cast by objects in higher dimensions, like a hand passing behind a curtain, visible only by the way it distorts the fabric. In this view, our entire universe might be a three-dimensional brain floating in a higher dimensional space, with dark matter's gravity seeping through from adjacent dimensions we can't perceive. Then there's the time angle. Einstein showed us that gravity warps spacetime, creating ripples that slow or speed up time depending on where you are. Could dark matter's influence stretch further, literally altering the flow of time in its vicinity? In regions dense with dark matter, clocks might tick imperceptibly slower, or particle interactions could unfold at different rates. This wouldn't just rewrite the rules of cosmology, it could explain why dark matter seems to know where to clump before galaxies form, as if it's responding to gravitational cues from the future. The implications are dizzying. If dark matter exists partially outside our dimensional framework, it might not obey the same laws of cause and effect. A particle could appear to vanish in one place and reappear in another, not because it moved through space, but because it slipped through a fold in time. Some theories even propose that dark matter's apparent stability isn't a property of the particles themselves, but of their position in a higher dimensional lattice, like a knot tied in a fourth-dimensional rope that never loosens from our perspective. Of course, testing these ideas is a nightmare. How do you detect something that might not fully exist in your frame of reference? One approach looks for subtle inconsistencies in the cosmic microwave background, anomalies that could hint at gravitational leakage from other dimensions. Another searches for tiny variations in the decay rates of radioactive elements on Earth, which might fluctuate if time itself flows differently near dense dark matter structures. So far, the results are inconclusive, but the hunt is far from over. The most tantalizing clue might come from black holes. These cosmic vacuum cleaners don't just swallow matter, they warp spacetime so severely that time effectively stops at their event horizons. If dark matter interacts with black holes in unexpected ways, perhaps clustering near them in patterns that defy classical gravity, it could be a sign that both are tied to deeper, hidden layers of reality. Whether any of these theories hold water is still unknown, but they force us to confront a humbling truth. The universe's greatest mysteries might not just be about what we can't see, but what we can't even conceive. Dark matter could be the first thread in a tapestry woven from dimensions and timescales beyond our own, a whisper from a reality where the rules are stranger than we've dared to imagine. And if that's true, then solving its riddle won't just reveal what's missing in our cosmic ledger. It might crack open the very nature of existence itself. There's something deeply unsettling about the voids between galaxies, not just because they're empty, but because they might be too empty. These cosmic deserts, some spanning hundreds of millions of light years, are the universe's quietest neighborhoods where galaxies are few and far between. But here's the catch: according to dark matter models, even these voids shouldn't be quite as barren as they appear. The gravitational pull of dark matter should have dragged at least a few galaxies into these regions, like leaves settling into the dips of a pond. Instead, some voids are eerily desolate, as if something swept them clean, and no one knows why. Take the Boötes Void, one of the largest known structures of its kind. Stretching roughly 330 million light-years across, it contains only a handful of galaxies where simulations predict there should be thousands. It's like walking into a stadium built for 50,000 people and finding only 3 spectators scattered in the stands. The discrepancy is so glaring that astronomers have spent decades scratching their heads, wondering if dark matter behaves differently in these regions, or if our understanding of voids is fundamentally flawed. One possibility is that dark matter isn't distributed as smoothly as we've assumed. Instead of filling space like an invisible fog, it might clump into ultra-fine filaments too faint to detect, leaving some voids emptier than expected. Imagine a spiderweb where some strands are thick and others nearly transparent. Galaxies would cluster along the dense threads, while the gaps between them stretch into true nothingness. This could explain why some voids look underdense, not because dark matter is missing, but because it's woven into a network we're only beginning to map. Then there's the wild card of dark energy. If this mysterious force pushing the universe apart varies in strength, it might have accelerated the expansion of voids more aggressively in certain regions, stretching them into extreme emptiness. Picture blowing up a balloon with weak spots. The thinner patches would inflate faster, leaving them more hollow than the rest. If dark energy interacted with dark matter in unexpected ways, it could have sculpted these voids into deeper, darker chasms than our models predict. But the plot thickens. Some voids aren't just empty, they're cold. The cosmic microwave background, the afterglow of the Big Bang, shows subtle temperature dips in these regions, as if the lack of matter somehow chilled the space itself. This integrated Sachs-Wolf effect hints that voids might be tugging at photons in ways we don't fully grasp, their gravitational pull or lack thereof leaving fingerprints on the oldest light in the universe. If dark matter's gravity isn't working as expected here, it could mean we're missing a critical piece of physics, the most tantalizing and unsettling theory. Voids might be evidence of something beyond dark matter and dark energy, a third dark component, an unknown force or particle that actively suppresses galaxy formation in these regions. It's a radical idea, but the universe has a habit of outrunning our imagination. Until we solve the riddle of these ghostly voids, they'll remain cosmic blank spots, not just in the sky, but in our understanding of reality itself. We think of the universe in terms of heat and cold, pressure and motion. But what if dark matter defies every rule we know about energy and temperature? Thermodynamics governs everything from steam engines to supernova, yet we've never stopped to ask, does dark matter even play by these rules? The idea of invisible particles carrying heat or entropy sounds like science fiction, but the implications could rewrite physics. Imagine a substance that doesn't radiate, doesn't collide, doesn't even friction, yet might still have its own hidden form of thermodynamics, operating in shadows beyond our perception. Take temperature first. In our everyday world, temperature measures how fast particles jiggle, but dark matter doesn't seem to jiggle at all, or does it? Some models suggest certain types, like warm, dark matter, might have just enough motion to resist clumping at small scales, subtly altering how galaxies form. If true, this would mean dark matter has a kind of temperature, not in degrees we can measure, but in cosmic consequences. It's like trying to describe the warmth of a ghost by watching how it makes the curtains flutter. Then there's entropy, the universe's obsession with disorder. Normally, entropy increases as energy spreads out. Think of an ice cube melting into a puddle. But dark matter doesn't behave like normal matter. If it never collides or exchanges energy, does its entropy even change, or is it locked in some perpetual, unchanging state, like a frozen river that never flows? The answer might lie in black holes. When dark matter falls into these gravitational pits, does it carry entropy with it? Some theorists argue that dark matter's information could be scrambled into Hawking radiation, a faint hiss of particles leaking from black holes over eons. If so, dark matter might not just have entropy, it could be quietly shaping the universe's ultimate heat death. the wildest possibility, dark matter might not just have thermodynamic properties, it could ignore them entirely. Imagine a substance so alien that concepts like hot or cold simply don't apply. In certain quantum gravity models, dark matter interacts with spacetime itself, warping the fabric of reality without ever transferring energy in ways we'd recognize. It's like trying to measure the temperature of a shadow. The tools we have might be fundamentally mismatched to the task. The stakes are higher than they seem. If dark matter has thermodynamics, even of an exotic kind, it could explain why galaxies cluster the way they do, or why the cosmic web looks so finely tuned. But if it doesn't, if it's truly outside these laws, then we're staring at something even stranger. A cosmic architect that builds without energy, sculpts without heat, and weaves the universe's grand design in perfect, impossible silence. What if we're not the only life in the universe, just the only life we can see? The idea that dark matter could harbor its own forms of existence is one of the most daring speculations in modern science. Not life as we know it, of course, no cells, no sunlight, no chemistry based on carbon and water. But if dark matter interacts with itself through unknown forces, who's to say it couldn't assemble into structures complex enough to mimic what we call alive? Imagine a civilization built not from atoms, but from particles that barely touch our reality. These hypothetical beings wouldn't live on planets, but in the vast, diffuse halos surrounding galaxies, drawing energy from dark matter annihilations or the gravitational tides of merging black holes. Their perception of time and space might be utterly alien. With no light to guide them, they could navigate by sensing distortions in spacetime itself, like celestial bats echolocating in the cosmic dark. The concept isn't entirely far-fetched. We already know complexity arises from simple rules. Think of how hydrogen and gravity conspired to birth stars and galaxies. If dark matter has any form of self-interaction, even subtle, it could theoretically organize into patterns. Some models suggest dark atoms could exist, bound by dark photons into exotic molecules. Others propose sprawling dark matter crystals, vibrating in rhythms we'd never detect. At what point does organization become sentience? We have no framework to even guess. Critics argue this veers into fantasy without energy exchange or information processing. How could anything resemble life? But nature has a habit of surprising us. Lichen survives in Antarctic ice. Bacteria thrive in nuclear reactors. Life on Earth flourishes in places once deemed impossible. If we broaden the definition of life to any self-sustaining, evolving system, could dark matter's gravitational dances, its halos merging, filaments twisting qualify as a kind of cosmic metabolism? The real mind-bender we'd never know. Two dark matter civilizations could occupy the same space as ours, overlapping like ghosts in a hallway, entirely unaware of each other. Their greatest monuments might be gravitational echoes, the wake of a galaxy collision, the ripple of a neutron star's death, events we'd attribute to physics, not culture. And if they're out there, they're likely just as oblivious to us. After all, to creatures woven from the universe's hidden threads, the glittering galaxies we call home might be nothing more than faint gravitational whispers in the dark. In the silent depths of the cosmic dawn, long before the first galaxies fully formed, the universe left us a cryptic voicemail, a faint radio whisper that shouldn't exist. This is the 21-centimeter absorption anomaly, a signal from primordial hydrogen that has scientists questioning everything they thought they knew about dark matter's role in the universe's infancy. Detected by the Edges Radio Telescope in 2018, this unexpected dip in the cosmic radio background suggests that the earliest hydrogen gas cooled too fast, as if something was sapping its heat long before stars had a chance to warm it up. Here's why it's so baffling. When the universe was just a few 100 million years old, neutral hydrogen atoms should have absorbed specific wavelengths of ambient radiation, leaving a fingerprint in the 21-centimeter band. But the signal edges found was twice as strong as predicted, implying the gas was far colder than models allowed. The discrepancy is like opening your freezer to find it somehow colder than absolute zero, a thermodynamic impossibility unless an unseen force was at work. Enter dark matter. One radical theory proposes that dark matter particles interacted with this primordial hydrogen, acting like cosmic ice cubes to chill the gas through collisions. It's a startling idea because dark matter famously doesn't interact with ordinary matter except, perhaps, in the universe's most extreme infancy. If true, this would mean dark matter isn't just a passive scaffold for galaxies but an active participant in the cosmos's thermal history, with properties far stranger than we've imagined. But not everyone's convinced. Critics point out that the signal could just be terrestrial interference, radio noise from Earth muddying the data. Others suggest less exotic fixes, like tweaking our models of early stellar radiation or accounting for unexpected magnetic fields in the ancient cosmos. Yet the most tantalizing possibility remains. This anomaly might be our first glimpse of dark matter's non-gravitational face, a fleeting moment when it reached out and touched the visible universe before retreating into shadow. The hunt for answers is heating up. New telescopes like the upcoming square-kilometer array will scan the 21-centimeter signal with unprecedented precision, searching for corroborating patterns in hydrogen's primordial hum. If they find matching anomalies, it could confirm dark matter's brief but dramatic cameo in the cosmic dawn, a role we never knew it played. What makes this mystery so electrifying isn't just the potential discovery, it's the implication that dark matter might have once been more than invisible mass. It could have been a sculptor, a choreographer, even a tempestuous partner to ordinary matter in the universe's earliest acts. And if it left fingerprints in the light of the first atoms, who knows what other secrets are hiding in the static of the void? The universe is expanding faster every moment, galaxies drifting apart like leaves on a receding tide, but what happens to the invisible glue holding it all together? Dark matter's ultimate fate hinges on a cosmic tug-of-war, a battle between gravity's pull and the relentless outward push of dark energy. Will it fade into obscurity, crumble into radiation, or outlast everything else in the cosmos? The answer could rewrite the universe's final chapter. Right now, dark matter dominates the cosmic scales, its gravity weaving galaxies into the vast web we see today. But as space stretches, even this hidden scaffolding faces an existential threat. In one scenario, dark matter particles could decay over astronomical timescales, slowly dissolving into lighter particles or even pure energy. Imagine a sandcastle crumbling grain by grain, except each grain is a particle that's anchored galaxies for billions of years. Some theories suggest this decay could be triggered by quantum tunneling, where particles spontaneously vanish from one state to another, leaving behind a faint echo of radiation. If true, the far future might see dark matter's grip weakening, its halos evaporating until galaxies spin apart like unspooled thread. But there's a twist: dark matter might not decay at all. If it's truly stable, as many models assume, its gravitational influence could persist even as the universe expands into emptiness. Picture a dance where the dancers drift apart, but the floor beneath them remains. Dark matter's halos would grow more diffuse, but their mass wouldn't vanish, meaning galaxies, or what's left of them, might still feel ghostly tugs in the darkness long after their stars have burned out. Then comes the wild card: dark matter might not just endure, it could thrive. If dark energy's repulsive force weakens over time, gravity might regain the upper hand. Dark matter's clumps could reassert their dominance, pulling scattered matter back into collapsing structures. It's a cosmic boomerang effect where the universe's expansion reverses course, and dark matter becomes the architect of a new cycle of collapse and rebirth. Some speculative models even suggest dark matter could seed a future Big Crunch, the mirror image of our Big Bang, where everything contracts into a singularity once more. Yet the most unsettling possibility: dark matter and dark energy might be locked in a feedback loop we don't yet understand. If dark energy's strength is somehow tied to dark matter's density, the two could dance in unpredictable ways, accelerating expansion in some eras, slowing it in others. The universe's distant future might not be a simple fade to black, but a chaotic seesaw between emptiness and resurgence, with dark matter at the center of it all. The irony is palpable. The same invisible substance that sculpted the cosmos could one day unravel it or rebuild it, and we're left with a haunting thought. By the time the answers become clear, there may be no one left to witness them. The universe's greatest architect might also be its last surviving ghost. Buried under a mile of rock in a former gold mine, shielded from cosmic interference by layers of earth and water, lies one of humanity's most delicate machines, a vat of liquid xenon so pure it might finally catch what generations of telescopes have missed. The lux-zeplin experiment represents the bleeding edge of dark matter detection, a 10-ton timepiece ticking in the dark, waiting for a single, infinitesimal collision that could rewrite physics. Yet despite its precision capable of sensing a particle's whisper-like impact, the detector remains stubbornly silent. And it's not alone. From the depths of Italy's Gran Sasso Mountain to the tunnels beneath South Dakota, a global network of experiments like Xeno NNT, Panda X, and Dark Side are all chasing the same ghost. The question isn't just whether they'll succeed, it's why, after decades of refinement, dark matter still slips through our grasp like smoke through a sieve. The challenge begins with dark matter's elusiveness. Unlike neutrinos, particles that rarely interact but leave faint trails in supercooled chambers, dark matter might not interact at all except through gravity. Most detectors rely on the hope that a dark matter particle, perhaps a WIMP, will occasionally bump into a xenon or argon nucleus, creating a flash of light or a trail of electrons. But these interactions would be absurdly rare. Imagine tuning a radio to a frequency where only one station broadcasts, and that station airs just one note every 1,000 years. Now imagine listening for that note while earthquakes, thunderstorms, and passing trucks drown out the silence. That's the noise floor physicists face, where cosmic rays, radioactive decay in the detector's own materials, and even the faint glow of potassium in a researcher's banana lunch can mimic dark matter's signal. This is why location matters. Laboratories like SURF in South Dakota or LNGS in Italy aren't just underground. They're encased in layers of geological armor, with water tanks, lead shields, and copper chambers filtering out interference. Lux-zeplin xenon is so meticulously purified, it's among the cleanest substances on Earth, with impurities measured in parts per trillion. Even then, the experiment must distinguish potential dark matter hits from background noise using fiendishly complex algorithms. It's like trying to hear a pin drop in a sandstorm by analyzing the sound waves of every grain. But what if the problem isn't just sensitivity, but strategy? Most detectors assume dark matter particles are heavy, sluggish, and interact via the weak nuclear force. Yet if dark matter is lighter, faster, or interacts through unknown forces, these experiments might be blind to it. Think of it as setting up a net to catch boulders, only to realize you're hunting fireflies. Alternative approaches are rising to the challenge. Superconducting sensors like those in the Sensei experiment hunt for lighter dark matter by looking for single electron excitations, while quantum devices like those in the ADAMS project search for actions converting into microwave photons in strong magnetic fields. Every pivot reflects a growing desperation, or perhaps creativity, in the face of dark matter's refusal to conform. The stakes couldn't be higher. Each null result narrows the hunting grounds, excluding swaths of theoretical possibilities like a cosmic game of battleship. Some theorists whisper that we might need entirely new physics, not just new detectors, to solve the puzzle. Others argue the answer lies in scaling up. Next-generation projects like Darwin aim for xenon pools 50 times larger than lux-zeplin, turning the volume knob to 11 in hopes of catching that 1 in a trillion interaction. But even these might not be enough. The irony is crushing. Dark matter outweighs visible matter 5 to 1, sculpting galaxies and bending light across the cosmos, yet here on Earth, it remains as intangible as a rumor. Every experiment is a bet against the universe's stubbornness, a wager that human ingenuity can outwit a substance that spent 14 billion years hiding in plain sight. And until one of these bets pays off, we're left staring into the void, wondering if the ultimate discovery awaits, or if dark matter's greatest trick is making us chase shadows forever. From the ghostly halos enveloping galaxies to the unexplained voids stretching across cosmic deserts, our journey through the 25 mysteries of dark matter reveals just how much remains hidden in the shadows of the universe. We've traced its gravitational fingerprints in the way galaxies spin too fast, in the paths of colliding clusters, in the ancient light of the cosmic dawn, yet every answer only deepens the enigma. Is dark matter a sea of undiscovered particles or a flaw in our understanding of gravity itself? Does it whisper to us through anomalies like the DAMA signal, or taunt us with its silence in caverns of liquid xenon? Could it be sculpting time, hiding in dimensions beyond our perception, or even, dare we imagine, harboring its own unfathomable forms of existence? The sheer breadth of these questions is humbling. Dark matter isn't just a puzzle, it's a mirror reflecting the limits of human knowledge. For all our telescopes, simulations, and subterranean detectors, we're still like astronomers from centuries past, charting the motions of celestial bodies without knowing what they truly are. The difference, this time, the unknown isn't just in the stars, it's woven into the fabric of reality itself, invisible yet undeniable, absent yet everywhere. And that's where the real excitement lies. Every unexplained rotation curve, every anomalous lensing effect, every void that defies prediction isn't just a gap in our understanding, it's an invitation. An invitation to rethink physics from the ground up, to question assumptions we've held for generations, to imagine a cosmos far stranger than we've dared to dream. Dark matter isn't just hiding the truth from us, it's offering us a chance to rewrite the rules. So stay curious. The next breakthrough might come from a lab buried deep underground, a telescope staring into the primordial universe, or a mathematician scribbling equations that no one else yet understands. Because if history has taught us anything, it's that the universe loves to surprise us, and dark matter, the ultimate cosmic trickster, might just be holding the greatest surprise of all. The day we finally grasp its secrets could be the day physics itself steps into the light. Until then, the mystery endures, and what a glorious mystery.